question messages, I'll like look into it. Okay, fine. So now for this session, like what we'll try and cover is like whatever topic we discussed in the morning that we need to cover is, and that had few topics of. So we saw a deep plan and all arguments. So what the last thing that we are left with is in deep plan is summarize. Like I didn't know, like we have missed it, but summarize is left with. Okay, so how do we use summarize quickly? Summarize is one of the grammar of dplyr. Okay, and what we do is like if I want to perform and if I want to see any customized statistical like values, okay, which is not there in summary. Okay, if you must be aware of the summary, I discussed this in the morning as well. Summary. Okay, if you want to do something on the data frame, on the entire data frame, so you can do this way. You just write summarize dataset name. Okay, if you want to see the delay, let's say that there's a new column you want to see delay, it's equal to mean departure delay. Okay, so what will happen, it will take the mean, it will aggregate it actually. That is the beauty, it will aggregate it on that column, and it will give you the mean of the departure delay column. Departure delay is one column. Okay, and na.rm is like if in case it has any nas, it will remove that na. Simply run and check, you will understand. See here, so it aggregated the entire data set. Like you had around 3,36,000 rows. Okay, it aggregated it, and it aggregated to a single value, that is delay, which you have created. This is the delay column that you have created. See here, check here. Okay, and what it did is it took a mean of departure delay, and it gave you the value. So this is the mean, and this is not possible in any like inbuilt summary or something in R. Okay, and how it is helpful now, if I want to know what is the mean of departure delay or departure arrival, anything, let's come to data set. Okay, now I want to know what is the average hours of a flight, average hours of a flight. Okay, so in this case I can just summarize, I can create a new column and summarize the row. Sorry, summarize the column, and you'll get the value. So let's have a look how it works. It works like this way. So let's say summarize, give the dataset name flights. Okay, and let's say av average flight, average duration, let's say duration. Okay, and what I'll do is, sorry, average duration is equal to you just check out the mean. What was the column name? Column name was hours. Okay, I'll just write hours. I just remove the na.rm is equal to true. Okay, and check the value. What is this? Sorry, it has an extra bracket. Remove this bracket. Remove this bracket. See here. So the average flight hours is 13.18. Okay, so you got to know that the all the flights. So if you have hours, 5 hours, 4 hours, 6 hours, but on an average there might be some flight which is having average flight hour of 30 hours, 40 hours, and that is why the average is coming to be 13. Okay, getting the point? Yeah, so R3, so the work of na.rm is to remove any missing values if you have in the dataset. Okay, so instead of handling it, we are just removing it for our like sake of easiness. I'll just get whatever value I'm getting here. So it is removing all the columns where the values of this hour is any. And in this case, wherever the value of the departure delay is any, it is removing and then calculating the mean. Otherwise, the value of column will be NA. Okay. That is it. So this is how we use summarize. Okay, it's a very easy and useful thing. So you can have a look. I'll share the code after the session. Now let's move ahead quickly and see something very like this will be useful when you start writing code, right? So it like instead of writing big codes, you make it. This is a shorthand actually. Okay, so we call it a pipe operator. So pipe operator is one of the agenda that I pointed out. So pipe operator. Okay. Now, let's say I want to count. I want to create a variable. Okay, and let's say I want to count the number of uh, diamond is my data set. Let's consider diamond is one of the data set we have. Diamonds. Okay, so let's see what is there in diamond. So it has all the variety. Okay, cuts. How many cuts it has? Color, clarity, depth, table, and all that value you have. Okay. Now, if I want to count it, so how will you use it? One case will be like this. So count diamond dollar cut. Sorry. If you see end row, so it will give you what is the problem? It's giving you null because there must be some missing value. Okay. Uh, end row diamond. Yeah. So if I take the count of diamond, how many rows it has? So it has 53,000. Okay, 940 rows. There's a shorthand of this. Okay, and we write this pipe operator. Now here, what is the advantage that you write the dataset name once? Okay, this is where we write the dataset name once. Okay, and then we write pipe operator, and then we count the whatever variable we want to count. Count is one thing. So what will happen? Automatically, it will group it. So if you are aware of groups, group by, which we'll see in SQL sometime later in this session. Okay, we'll see a group by operations. So it is grouping each type of cut on a first thing. Since I'm counting cut, see, I have written count cut. So automatically it will group cuts like how many ideals you have. So it will filter out ideal. Then it will count ideal. So it has ideal. It is 21,000 times. Okay. Then it will filter out ideal and it will change it to premium. Okay, then it will count how many premiums. So automatically it will count the premium. So the thing is, for this simple thing which you are seeing here, you need, if you don't go in this if you don't use pipe operator, you might have to use a very lengthy 2 or 3 loops to count it. Okay, you need to group it, then you'll have to count it. Okay, but here in a single line of code, you can just provides you the flexibility of doing the same thing. Okay, so you'll get to see. And since this is again feature of dplyr, this pipe operator is a feature of dplyr. Okay, so here you can use all the grammars: select, filter, summarize. Okay, and all the other filters you can use, all the other grammars. So just take for example here. Now I'm providing this data set as an input. Okay, this is the input to my data set diamond. Now giving pipe operator, I want to filter all the caret whose value is less than 3. So what will happen in a diamond data set? All the caret which is less than 3 will get filtered out. We'll get only that value. Okay, so and I'm renaming it to a new variable called smaller. So if you don't want to rename it, keep it in a new variable, you can directly run this, so you get a output. No, we'll have to put it here in some variable to receive the output. Okay, so now if I check what is there in smaller, so you will have all the values, which is all the carrots which is less than 3. You don't get anything less more than 3. See here, carrot value. Okay, and you can if you see this example here, you can combine multiple pipe operators. Okay, and the only thing which you need to understand very carefully here is when you have multiple pipe operator like this. uh, Here we saw only one pipe operator, so we knew, yeah, this is getting executed, and your this same value is getting, this is getting executed, okay, on this data set. Okay, and then the value is getting assigned to this variable. This is a normal tendency and normal understanding that we go along. Okay, and that is absolutely correct. Okay, but things get little complicated when you have multiple pipe operators. Like here you see you have one pipe operator, then again you have one more pipe operator, one more pipe operator. So how actually it is happening? Okay, so it works in this way. It works in upside down. Okay, so this is the data set. This data set goes to this statement. Okay, and in this statement what I'm doing, I'm selecting columns. So if let's say I have around 2 to 4 to 6 to 8 10 columns here in my original data set, but I'm only filtering out 4 columns, 5 columns, sorry. Okay, so I'm filtering out 5 columns. So this 5 columns is going as an input to this statement. Okay, here what it is happening, it is getting filtered. This particular column price is getting filtered out, and the condition is less than 400. Okay, so the output of this filter will go to mutate now. Okay, and here what will happen, like all the value which is less than 400 in price, that will get divided, like depth is divided by table, and you'll get the another column. And just execute and see it. So the flow, I hope you understand the flow, like how it is getting executed. See here. So that all the four, only the 5 column is getting selected. First thing to observe, if you go sequence wise, 1, 2, 3, 4, 5. Okay, this 5 column was the original column that was there in the table. Okay, don't get confused with this, because this is a new column that is being created by mutate. Okay, this is the first thing cleared out. Second condition was less than 400. So price, go to price, and you see all the prices is less than 400. Nothing is more than 400. So this got satisfied. Okay, now the output of this goes to mutate. Okay, and you have a new column. So if you don't give a name, if you don't give a name, then by default it will take this as a name. So this is what happened. So by default this is a name here. Okay, and the value, this is getting calculated. The calculated value is here in this muted value. Okay, so the whole, and on a nutshell, if you try to understand this, if you try to do this, so what you'll have to do if you are not using pipe operator. Okay, just think about it. So it will happen like this way. X, you'll have to first select the columns. So these are the columns you are selecting, and this can be easily, you can break it, there's no harm in it, but just to avoid like in a real time, you need to avoid multiple codes, right? So this helps you in that. So I'll have to first select all the columns. Sorry, I'll have to mention that uh, data set as well. Select data set column. Okay, so I ran this. Okay, now the second is I'll have to filter out. So again I'll create a new variable y. Okay, where I'll filter things. Filter diamond. Hold on, guys, for 1 minute, guys. Hold on for a minute. Yeah. So what I was saying is, if I want to, this is not. It is not like you cannot perform this operation if you don't use pipe operator. You can do that. Okay. So if I compare it to what we do using a pipe operator and what we do not what we'll have to do when we do not use pipe operator, okay, just to differentiate between these two. So let's see step by step. So select statement, what I'll have to do is I'll have to write select statement, diamonds, and the columns that I need to select. Okay, this is the first step. I ran this and the value is in X. Okay, so now I'll have to use X as my data, input data, because the entire selected data is in X. So I'll use X now. Now I want to filter. What I need to filter is price. Okay, so X dollar price less than 400. This is my second filter, right? So I'll run this. Now the value is in a new variable called Y. Okay, now what is the third thing I'll have to apply is mutate. So let's take in a third variable Z. Now our input data will be Y. Okay, so mutate Y, and what I need to calculate is I want depth. So Y dollar depth divided by Y dollar depth by table, right? This. So this is my mutate. So finally, the output which I got here, I'll get it here in Z. So let's see what you have in Z, and this is what exactly you get in Z. So now if you compare both the results, they are exactly same. Okay, see here, they both are exactly same. Column names, a muted column is exactly same. Okay, just the difference in name, that is fine, it is doable. And then the column that I selected and the value that I have is exactly same. So you have around 247 into 6, 247 rows and 6 columns. That is exactly same here as well. Okay, now coming back to the code, see here, now here I have used only, data set is being used only one time. But in our case, individually I'll have to use different data sets, because each data set is getting assigned to a new variable, and that I'll have to use it. That is how it works. So in a long run, like when you have multiple, like 15 or 16 filters and field mutate and all that, so it becomes very cumbersome to use individual statements. And then in that case, it's very efficient, fast, and readable. You write one, this is one data set, and this is a sequence that it operates on. Okay, so just have a look and try and understand this pipe operator. This is very efficient and you love it actually. Okay, so if I can show you some more uses, it's not there. Yeah, so this the only thing is that this goes on increasing. The pipe operator is it goes on increasing. Later on you can add summarize on something. Okay, summarize on let's say uh, this is a variable you created. Let's see if it works or not. Let me remove this summarize. Okay, now if I see in X what I have, so the call, I've just renamed it. It exactly same what we have ran earlier. I'm just renaming this mutate to XX. Okay, depth not found. Where is depth, man? Okay, so this is giving you error. Fine, let me run it once again if it is. So you cannot rename it or what? Yeah. So this renaming is creating an issue. So you cannot rename it actually, I guess. No, so you cannot rename it. Okay, but yeah. So if sorry, this is the issue. You can rename it. So the extra pipe which I added for just sample that I have not removed, and that was raising an issue. Okay, so see here, I have renamed it, and where is the mutate? So that is not being displayed. So you cannot rename it actually. I guess that is the problem. Okay, so you'll have to use it as it is.
So is it necessary to use the
Necessary to use?
filter operator to use data, and then after filtering out we use the mutate operator, or can we use the mutate operator
It
first?
it is totally totally depends on what you want from your data set. Okay, so why I'm writing in this sequences, it sounds logical. Okay, first I'm selecting the column, then I'm filtering it out, then I'm creating a new column called mutate. But if in case you don't want to filter out, okay, so you can use this way. Or if let's say there's a situation where you want to filter the data. Okay, you want to filter it, and let's say you want to filter it on price only, price less than 300. Okay, so you can even do this will work. So it depends on what you want from your data set. Okay, so that is the only prime thing. This will work.
Thank you, sir.
Okay, so you get the output. So let's see, you get 0 as a result. That means that there is no condition. Like if I filter it out, let's see why it is so. Okay, investigate a little bit in this diamonds. Okay, uh, if I filter something in diamonds and I want price less than, why price? Okay, anyways, so let me first diamond price less than 300. Do we have anything as such? No, we don't have any. Okay, so that's why we are getting a like no output. But there is no sequence that is predefined. It totally depends on what you want and what's your requirement is. Okay, fine. So I guess we are done with deep layer now. So we are done with deep layer. Now let's start quickly with machine learning thing. Okay, so let me have a look. Just pause the recording for a minute. Understand the concept, and so if you have done your subject of econometrics, okay, so I guess some part of it, not exactly the entire thing, but some part of it will be covered there or must have been covered there if you have already done your econometrics subject. Okay, so let's start our discussion with the data. Okay, that is the like whole point where we talk about. So data, like in a raw form, what it is just a entry, it is a random entry or random record it has, and we'll have to work in a way to drive the proper and the best insight from it. That is what we want, and that is why the whole fight is all about, or that is the reason. Now when you take a data set, any raw data set, so in that you have variables. Okay, so variables is what in our local term you can call it a column. Okay, so you have multiple columns. So sometimes the column ranges from, let's say you have 2 columns, 3 columns. Okay, and it ranges to 200, 300, 400 as well. Okay, so now like analyzing the data set manually is fine, but when we go into machine learning, when we need to feed our data set to our machine learning algorithm, so algorithm is very stringent and very specified to what it accepts. Okay, so it accepts categorical variable, continuous variable, factors, integers, what it accepts. Okay, so it varies from algorithm to algorithm. Okay, and few things that is constant across algorithm. Okay, and one thing which I can tell you as part of our discussion, that is PCA, principal component analysis. So it is the the lesser number of column you give it to a algorithm, okay, the better it predicts. Okay, now lesser does not mean you'll have to be like just keep this thing in your mind, lesser. Okay, so less means like less also comes with important. Okay, the column which is a deciding factor, this which will act as a deciding factor for something. Now take example of uh, let's say Walmart, let's say pantaloons. In India, you have pantaloons, and pantaloons needs to predict what will be the sale in coming 3 months. Okay, and it has records, customer sales record from its different outlets in Kolkata. Okay, and what it has records has like person, customer name, customer ID, customer phone number, customer address as well. If you have a card that pantaloons, like they have a card, right? Loyalty card. If you have a loyalty card, you have everything. They have all the data with you: email ID, okay, address, phone number, how many times you have visited, how much you have spent, okay, all those. Then they have marital status or how many family members. All those things they can arrange it. Okay, now if I want to decide like overall sale of a pantaloon, okay, so I have that data set. That does not mean I'll push in all the data set to my model. Okay, that will give you a very like unbiased or biased result, you can call it, and that will not be a useful thing for it. Your model will predict wrong result. Okay, so in order to understand like which variable you should give it to a model and what you want, the ultimate thing is like what you are expecting from a model as an output and what data you want to put. So the relation between this is called the relation, you can say the analysis between this phase is called principal component analysis. Okay, PCA is used for PCA is a let's say a science where you try to understand the variable. Okay, and in that variable, which variable will be important or which variable will be significant to decide a particular result. That is PCA. Okay, and there are various ways that we do PCA. So some of them, they're straightforward. We do it manually. If you just think, import a data set. I have a data set and I see there are a number of columns. Okay, what I want to predict, I want to predict revenue. And this, I know that I want to predict revenue. So how many children a person has, that will not impact that revenue. Yeah. What is the salary of a person? What is the expenses of a person? How many car he holds? Okay, how many credit card he has? How many account he has? That will impact the revenue that he generates in a year. Okay, but how many like where he stays? Okay, how many children he has, okay, which car, like which type of car he owns. So that will have a very vital or very like that will not have a very vital or very negligible impact. So I'll remove that all that columns. So removing of columns, unnecessary column, is a part of PCA. Okay, now let's check a data set. You have a data set, this is again a very common data set, empty cars. Okay, so I'm getting a variable, I'm just selecting few columns. So I'm selecting first 1 to 4, 6, 7, 9, 10. So I've selected this variable. Okay, so there's a package here in R. So this is the column which I selected, which is used for principal component analysis. This package is used for principal component analysis. Okay, I simply give the variable. Okay, and what's your scaling parameter, center, true, scale, true. You just run this. This will get you get this in the document. See summary. So it will give you, this will basically give you the variable and the relation between them. Okay, so the how it ranges, it is, if it is approaching towards zero, that means variables are not correlated. If it is approaching towards like away from zero, that it is correlated. Okay, and you should keep the less correlated variable. For example, uh, take this example, like you earn rupees X. Okay, this is one source of income, and second source of income you are getting Y, and you have a summation of that is Z, X plus Y. Okay, so now you give X and Y as an input to a model, you get result A, but you are inputting two variable. But if you already have a column that gives you a total sum of your income, and if I input that variable into a model, again I get the same result. Okay, what does that mean? So that input, like sending two input variable is useless, because you can replace that with one variable. Okay, so this is how you can imagine. PCA is principal component analysis, the full form of PCA. Okay, so I just have a look to this uh, like package, or this is an inbuilt. You don't have to use any package in this. This will come by default in R. Have a look, and how do we select? That is the most important question. So when we do the algorithm, when we run algorithm, we'll get to see. But here, I just, for the sake of understanding, I what I did is I I created a subset of a variable. Okay, this is my subset. I inputted, like I'm importing this subset variable into a, like, to principal component. Okay, and then I check the like what is the correlation factor. So this is one way to analyze. Or what you do is, there are many variables. When I send you a document, so you'll get to know there's a variable called core. Okay, score gram. So it draws the what is the relation between each variable. It'll draw a graph and it'll show you. Okay, then there is one more function called prince prcom. We have already seen prcom. We have already seen. Then we have something called hmm, only core. Okay, so this is one variable. This is one function that to test correlation. Okay, and yeah. So the idea, are you aware? Like, so choreogram is a function that is used to get the correlation. Okay, the correlation factor. So what is correlation factor? Correlation factor is something which will enable you to decide what is the correlation between two variables. So for example, let's say the same example which I gave you. X is your income from, let's say, source 1. Source 1. Y is your income from source 2. Okay, Z is your income from source 1 and 2. Okay, summation, let's say summation of 2, or you can say 1 plus 2, something like this. Okay, now if I do any I'm let's say I build a model, linear model. Okay, where I'm trying to predict your upcoming, like, let's say I'm trying to predict your next year's salary or next quarter salary. Okay, salary. So if I input this X plus Y, I get some, let's say there are other variables as well, not only two. X, Y, you have A and all, whatever it is, A and B. So I get some result. Okay, but I see that this variable is correlated. The correlation factor is very high in these two variable. Okay, and you have one substitute, or you can create one substitute variable where you can sum this. Literally, this sounds same. Okay, and you can replace this with Z instead of putting in two. Instead of giving two variable as an input, you give only Z, and you get the improved result. So this is what is the science behind it? Because these two variables were correlated, and correlated variables were impacting your result. So you just remove that correlated variable and replaced it with another third variable which is exactly same. So it will give you the proper output. So now, to understand the literal meaning of it, okay, So literal meaning will be, you have, let's say, uh, the good example will be this. If I have a variable, let's say column name is column name, mm, yeah. So let's say employee. Let's, yeah, ARP. No, ARPO will be a technical term. Let's say salary again. Okay, and this is column one. Okay, let's make it small. Call two will be like a bonus. And there are likewise you have around 10, 10 called 10. You have called name 10. You have 10 variables. Okay, now what will happen when you build a model? Okay, let's say you are doing a linear modeling, and you found a linear model, and you gave a data set. This is a data set, and then you try to predict the, mm, let's say, next quarter salary or something. Okay, so predicted salary. Let's say you are trying to predict whether it is a male or not. Okay, based on salary, you have all the demographic details, and you need to predict whether it is a this person is a male or female. Okay, this is one good use case. Okay, so you have entered all the columns. Call name 1 plus call name 2, and likewise. Okay, likewise you have entered all the things till call 10. So you got some output. Let's say you got some output, model statistics. You got model statistics, something, some value. Now once you analyze your model, you have, before doing this modeling, you'd have not done any like correlation check or something. But you find you do a stepwise modeling. You just try to remove this column, and you build a model. Then you do a correlation check, and you see that column 1 and column 2 are correlated. Okay, so what does this mean? Like, put like they are correlated, so keeping both the variables is useless, because if one is going in one direction, the like both are parallel. I mean to say, each is having same impact. So you it can be a salary impact, it can be any kind of impact, but they are in the same direction. And if you remove one variable, and you find that the correlation factor is same for both. So if you remove one variable, and then you see the model output is better. Okay, so removing a correlated variable from the model will always improve your model output. Okay, model efficiency. That is the whole idea of correlation and PCA. So now if I the document which I'll send you on correlation, okay, it has few use cases, a sample use cases. Just go through it, and you will be very clear on what PCA and correlation is. Okay, guys, any question on theories? So if I talk about machine learning algorithm, okay, so machine learning algorithm is broadly divided into two part. Okay, and you will hear it from all, like you'll get this a lot. If you just Google it, you'll get to see n number of comparison and difference between these two. Okay, and this is a very good conceptual question when it comes to interview and all. Okay, so just have a look and we'll try and complete this and let me know if you have any doubts. So the first one is called supervised machine learning algorithm. Supervised ML algorithm. Okay, algos. The other one is called unsupervised. Unsupervised ML algos. Okay. Now, how do we difference? What is the difference? That should be a question. Okay. So I'm naming some of the algorithm. Let me know if you have heard about it at least. Okay. Linear regression. So linear regression. Then you have logistic regression. Okay. K-means algorithm. KNN. Okay. And you have any classification algorithm. Okay. So if you have heard about it, okay, then it will be very interesting. And if not, no issues. Okay. So there are two types of machine learning algorithm. One is supervised ML algos, machine learning algorithm. Another is unsupervised machine learning algorithm. Okay. Let's talk about the first section, linear regression. That is supervised. So why we call supervised, and what does the name imply? So supervised means you have a data set. Okay, you have a historical data where you can do your analysis, or you can do research on that, and based on the historical trend. Okay, so since it's, as you have the data with you, that what does it mean? It simply means that the event has already occurred. Okay, and that is the reason you have the data in your hand in the system. Okay, so this, and if since it is already occurred, that means it is a historical data, it has occurred in past, so you will not have a data that will happen, that you will not have a data of things that will happen in future. Okay, so that is not possible. So if you have a data set in your system, that means you have a record of something that has already happened. Okay, so you have a clear and concise data set. Now as you have a data set in your system, and you can use that particular data set to do what? To predict what can happen in coming days. Okay, that is called predictive analytics. Okay, you are trying to predict something. Okay, and how you are predicting? You are predicting using the historical data. Okay, the moment you have historical data and you can use that data to predict the upcoming upcoming events or upcoming days event. Okay, that is called supervised, because you have a clear path, you have a data set, you know what you need to predict, and you use some algorithm, like let's say linear regression, logistic regression, or any predictive modeling algorithm, time series forecasting. Okay, and you can predict coming event. So in that case you have a supervised machine learning algorithm, that is called supervised. But in case of unsupervised, you don't have a data record. So how does it happen? Let's say you are getting a calls. Let's say you have a call center, uh, in your you work in a call center company that receives lots of calls. Okay, and you don't know what, like people are calling for what reason. Okay, there are a number of people calling for x number of reasons. Okay, but on a real time, if you want to know the reason, you will have to segregate. And how will you segregate? You will segregate using the text or the words each text or voice has. Okay, let's say someone is complaining about wrong bill, someone is complaining about bad service, someone is complaining about bad network. Okay, so you on a real time, the segregation is getting created. Okay, so if things happens is in a way where you don't have historical data and it happens on a real time, okay, that is called a classification problem. So in that case we call it unsupervised machine learning algorithm. Okay. Now, a good example from a very day-to-day life. Now, you open you always, we all use Gmail, right? Now, Gmail we use, so if you are aware of, so let me open a Gmail. So if I open Gmail, if I open a Gmail, if you send me a mail, okay, so your mail will automatically come in primary. I'll receive it somewhere here. Okay. Now, if I do some activity on Facebook and from there if I get a mail, so my mail is automatically coming in social. Okay. And if someone sends me a promotion mail, okay, that automatically comes here. Correct. So do Gmail already knows that who is going to send me a data, and based on that they have created a 3 tab, and I am getting this? No, right? This is happening on a real time. So the moment mail comes in a server, okay, what text it has, what is the context of the mail, based on the context it gets, like it gets routed to a particular folder. It comes into email if it is a normal email. If it is social mail, it will comes to social. If it is a promotion, it comes to promotion folder. Okay. So this is happening on a real time, okay, without any prior data. And this is classification problem. It is getting classified into different sectors, different sects. Okay. And this is called unsupervised machine learning. So the algorithm which is working in this Gmail inbox is unsupervised machine learning algorithm. Okay. Clear? Now if you want to see any forecast, okay, so see here, if I open a forecast graph. So if I open a forecast thing, and I see that they have forecasted, today is 27th, Saturday, they have forecasted till 17th of like February. No, sorry. Yeah, somewhere. Till, let's say for a week. So how it is doing? It is doing using a historical data. So they are using a historical data, or whatever data they have, okay, and trying to predict the upcoming event. So this is a supervised example. So clearly, you should have a clear indication, or clear and concise distinction factors. How do we classify algorithm as a supervised algorithm, or how we classify algorithm as a unsupervised algorithm? Okay, guys, any doubts in this? Any doubts? Quickly, we can have a question session. Then we can continue with the codes. Yeah. So can you see my screen? I'm sharing a whiteboard. Okay. Here, what we'll try see is linear regression. So how many of you have heard about linear regression? So now linear regression, as the name says, as you already know, it is classified as a supervised machine learning algorithm. Okay, and you'll get a list here. If I open this and show you which algorithm falls where. So if you see my page here in Facebook, so I've created one. It's a little slow here, so let me check in Google. Yeah, not this. Sorry. Uh, not coming here. Let me check. You can look at this picture. This is very helpful. You'll get all the algorithms which is supervised and unsupervised. It is classified here. Okay, so supervised machine learning algorithm. Okay, you have regression techniques, you have classification techniques, then you have unsupervised, then dimensional reduction, clustering. Okay, then reinforcement is something which is like very it is advanced topic, that is artificial intelligence and all that. Okay, you can use this image to just learn it. It is very good. And the other one which I was referring to was, it's not there. I'll try and send you. Okay, it's not there now. Anyways, it is I'm not getting it right away. I'll try and send you. Okay. So what I was telling is, be clear on this, and let's move to our discussion on the whiteboard. So there are a list of algorithms that automatically falls on supervised, and there are some which falls on unsupervised. Okay, so linear regression, which will start now, is that falls in a supervised machine learning, linear regression, logistic regression, these two. So if we talk about linear regression, so linear regression is a very basic algorithm, machine learning algorithm that we use. And now, how do we use it? So the core idea will be, let me remove this everything. New sheet, clear. Okay. Now I have a, let me create a data set. You have X. So you have X, and then you have Y. Y. Okay. So X is some value, let's say sales, and you have Y as a revenue. And there are various entries. Okay. Let's not talk about the entries. Now you plot this, you have plotted this entire thing into a graph. This is your X and this is your Y. This is your Y. Okay. So this is sales. Let's put this here as sales. And this is your revenue, normal revenue. Okay. Now, if you plot a graph, let's say you have a data set, and in that data set, you are plotting a graph, and the graph somewhat looks like this. Let me make it. Okay. Somewhat looks like this. Let's say you plotted it something like this. This is the data points. So different data points. So obviously you'll have to check outliers and all. That is a normal process. If you again refer to the Facebook page, there's a image, 7 the steps that you need to do before performing machine learning. So this is the normal plots you have. This is a sales plot. You have a XY, as that is sales and revenue. You plot it in a XY plane, and this is the plot you have. So what does this linear regression does? Okay, so linear regression, if you can recall it from your earlier mathematics, so we had equation is equal of a symbol single line, okay, that has y is equal to m, where m was your slope, x was your x-axis, plus a constant variable called c, constant called c. This was the equation of a line. Okay, okay, so this was the equation of a line. So this is linear regression. So we call it, since it is linear in nature, so we call it linear regression. And why regression? So regression because it is regressing the historical data. Okay, that's why we call it a linear regression. Regress means like going through a, like passing through a data set. Regress means I'm trying to pass from historical data, and I'm going ahead to predict something. Okay, coming month, coming 2 month, coming 3 months of prediction I'm doing. So that's called regress. Okay, that is why it is called linear regression. So try and understand the equation here. So this is where the entire concept of linear regression, simple linear regression, lies. Your m is your slope, x is your x-axis, x variable, y is, and c is your constant. Okay, so now using this equation, let's say if I plot a line, so the line will somewhat look like this. Let's and this let's say it goes a straight line, and it passes through the maximum number of data points. Okay, maximum number of data points. Okay, this is the strategy. Okay, when you do linear modeling, so the linear modeling, the variable selection and all that you do, that has a core, like the agenda behind it, the core agenda behind it is it should pass to the maximum number of data points. Okay, so what we see is we see that it has a continuous increasing trend. Okay, if this is a slope, you see a continuous increasing trend. Okay, and you can here till here you had a data set, so you predicted. Till here you had a data set, you predicted. Okay, but for coming 2 months or 3 months or 6 months, you can even use this equation because it will some extent follow. If you do a straight line for another 2 months, 3 months, it should follow. Okay, now we'll see what this is. This is the difference of the data point which is not lying in the line, that is outside. All these points, you draw perpendicular from that point to a line, the straight line. Okay, this perpendicular from a data point to a straight line is called error term. Okay, since the line was not able to reach all the points, if it reaches all the points, so the line will look somewhat like this. It will not be a linear anymore, it will be something like this. It will try to reach, it will polynomial. Okay, it will be something like this. Getting my point? Something like this. If it tries to reach all the points, this will be polynomial, and there is no way to, we cannot define this in an equation. Okay, so this is impossible. So that's why we make it simple and we do a straight line, and that passes to a maximum number of points, and we calculate the error point. Okay, and the target of yours, okay, as a developer, as a data scientist, as an analyst, you should make sure that your error term is least. Error term, that is called e node, or you can call it big E, error, error term should be minimum. Okay, fine. Now, yeah, so that is error term. You have a linear line. Now, what you can do from this? How will it be helpful if you are taking such a huge effort, and you try? How will you get benefited? Now, see the line. If the cell increases, okay, if a cell increases, so let's say, let's not make it revenue. Let's call it as user. Okay, I'll just write this is advertising expense, advertise expense. Okay, so now using this chart, this is advertising expense, and this is sales. So anyone can say, let's say, if a sales, if a advertisement increases, if a company increases its budget on advertisement, okay, so it sees there's an increase in sales. Okay, this is what the graph and this line chart says. Okay, that is what your model is all about. Now let's say company has a budget for this year. Like this year they have 100 million, or let's say 10 million of budget in advertisement. Okay, now the company comes and asks the team, let's say today we decided on the budget of advertisement and that is 10 million. Now what should be the expected revenue that we should get? Okay, the company is asking. Now based on the previous records, a team will sit and they'll analyze it, like, oh, what was the previous earlier 2 years, 3 years of trend. Okay, and they'll come up with this chart. Now they'll go to the management. They'll say, if you are spending if you are spending 10 million, okay, this, let's say the 10 million is somewhere here. Okay, you'll probably get a sale of 150 million. Let's say this is 10 million. 10 million. Okay, and the expected return is $150,000. Okay, let's say 150 million. Not now, company agrees. Yeah, they say, yeah, I'm okay if I'm spending 10 million as per expected revenue, or the sale will be 150. Okay, now again they said no. I like we want. They came with the opposite scenario. They said no, 150 will not be sufficient for us. We want to increase. We want to have a sale of, let's say, 170 million here somewhere. 170 million, which is somewhere here. What should we spend? Because the management is asking, we need to have a sale of 170 million. How much they should spend on advertisement? So this is reverse engineering. They'll check again, if 170 million is the sell, they should spend how much? They should spend this much in advertisement. So they'll come and they'll say, so boss, you need to spend $13 million in advertisement. Okay, so how we are concluding and how we are using this is using this linear regression. You have a historical data, we do a model, we have to check the efficiency of the model very efficiently. Like if the model is perfect, it has less error term. Okay, after building a model, we saw the statistics, and then we use it like this way. What I said you is the user's perspective of it. Okay, now are you clear on this? Any doubts so far? Guys, any doubts? No. Okay. Okay. So, fine. So before we go ahead with the code, I'll just try and check. I'll tell you all the technical terms that we have here. Okay. First, we have seen error term. Okay. And what is error? I've told you. You'll get something called mean square error. Square error. Okay. Absolute error. Then you'll get absolute mean square error. So since we have such a variety of error terms, so you can understand from this how vital this error is. Okay, we cannot ignore it. We'll have to understand it. Okay, then x and y axis, slope, okay, fine. So let me discuss this. Normal error is simply a perpendicular line drawn from the your straight line, that is linear line, to the data point. Okay, if this is 4, if you are considering, if the system you not wanted to calculate individually, that is impossible. Okay, if your tool is considering the points above it as a positive, then obviously it will consider the points below the line as negative. Okay, so there's no hard and fast rule, but positive, this is positive above, will be considered as positive, then obviously below the line will be considered as negative. Okay, so this error terms, ultimately, if this is positive, all the positive will get added, all the negative will get added, then summation of that is your error. Okay, summation of positive and negative, summation of error above the line and below the line will give you the error. Now mean square, so there is a problem with this error term. Okay, if you just simply take the error, that means summation of positive and summation of negative, there is a high chances that this has a positive magnitude, this has a negative magnitude. Okay, they sum it and they become less. Okay, if positive side is more and negative side is less, so they'll become less in magnitude, so you will not be able to gauge or measure the exact error term. Okay, so at times this come as a concern, so we don't take this normal error, we do not go for a normal summation. Okay, so that in that time that mean square error comes into picture, so all the error is getting squared up and then it is getting added up. Okay, that is one thing. Now in absolute, what happens, the irrespective of positive or negative, you just take the value of it. Okay, don't take the sign, and then you get added. So once you run the model in R or wherever SPSS, so they'll give you various, you have a error term, this mean square, absolute error, mean absolute error, they'll give you various errors. So whatever you want to consider, you can consider it. So there's like just to understand what it implies, so it implies this. Okay, absolute means they'll take the only the positive value, they'll not take the negative value. Okay, so obviously if they're taking one sign, positive only, then the magnitude of it will be more. Okay, fine. So let's move ahead with the coding stuff. I'll go to R. Okay, there are many examples that we'll see, but for now, let us have quickly look into one small example, because most of the things will come in assignments. Okay, you will get a data set, and you'll have to implement linear regression in that. So here what I'm saying is I have a data set called US judge rating. Okay, so it is again inbuilt data set, US judge rating, it is there in R. Have a look. Okay, now how does the data look? The data looks like this. So you have a person name, and like how many times like this is judge name, and the rating that is that has been given to him or her. Okay, what is the column names I have? Call names, US judge. These are the different column names. So what is the number of columns, and call US judge. We have 12 columns, right? So that means 12 variables you have. Correct. Now, before we actually do modeling, let me ask you to have a look. LM. LM is called used for linear model. Then again, you have some another variety of it called as GLM, general linear model. Okay, you can use both. Probably for this example we'll use LM, but now onwards or tomorrow onwards, where when you do a like assignments or problem, so use GLM, it is good. I don't know the difference, but GLM is better actually. Okay, so this is how we use it. There's a straightaway formula. There's, I'll tell you, in modeling, in machine learning, 80 to 85% of the effort and the task, or you can say the brain, goes in data preparation. data pulling, data preparation, okay, handling missing data. Then comes principal component analysis. Then comes correlation check, okay, multicollinearity check. This will consume 80% of your effort, 75% of your effort. And implementing, once you have the data ready in your system, once you have data ready, it hardly takes a minute to implement the model. And you can see it here how easy it is. LM, put the variable you want to predict, and all variable which is you want to use. Okay, so this is how, like, this is the way we implement, and this will be remaining same across all the data set. There's no, it is not going to change. I mean, the way we implement machine learning algorithm, that is not going to change. Okay, now the one of the important thing which I missed to discuss here was here, this equation which you see here, y is equal to mx plus c. Okay, so there is something y, okay, and there's something called x. So generally we represent this as a small y and small x. Okay, now what is a small y? Y is your what? Y is your dependent variable. Okay, just have a look, guys. This is very confusing at times. Okay, variable, and x is your independent variable. Okay, now how will you decide if you have a new data set? If you are given with a data set and you need to implement linear or logistic, okay, this will remain same. The entire concept will remain same in linear and logistic. Okay, so how will you decide? So any time when you have a data set and you need to predict something, so you are going to predict some particular column or some particular, yeah, some particular variable. So the variable which you are trying to predict is always going to be your dependent variable. Okay, because that particular variable is depending on some factors. Now if I see here, since I have given you the both way around example, so it might confuse you, but see in a state of it direction, and think like, if I want, this is my y, advertisement expense is my y. If I want to predict this, so x is my independent variable. So x can take any value. Okay, the variable which can take any value will be your independent variable. Okay, now we'll have a very general example in a university. Okay, let's say you have a capacity of 180 students. Okay, now your grade, you'll get A, B, C, D is a grade. Okay, and I need to predict this. And what I have is, let's say I have 10 variables from each students. For each students, I have a 10 variable. So I have their undergrad marks. I have their semester-wise marks of first, second, and third semester. Let's say I want to predict 4 semesters grade. Okay, so I have 3 semesters marks. That is 3 variable. Undergrad marks, fourth variable. Their attendance, fifth variable. Okay, then there are other things that I can have, projects, their assignments, their lab marks, and let's say I have total 10 variables. Okay, so, and what I'm trying to predict is only one variable, which is what will be your fourth semester grade, final, the master's fourth semester grade. So all the values, the lab assignments, attendance, percentage, they can take any value. Okay, for me, but my what I'm trying to predict is that is dependent. My grad marks, first semester grad marks, is depending on all the independent variables. Okay, you can take this example and learn it actually, what is dependent and what is independent. Okay, and if you have any question, you can ask me right away before we proceed on. Sorry. So this part is missed. So yeah, so I'll try and record it and send it to you. Okay. Yeah. So you know what is continuous and categorical data, guys? Fine. So what we'll do is, let's keep it till now, here till now. I'll send you the recording and assignments.